Hello? Oh, are people there? Hello?
Hey.
How's it going?
Fine. It's been a long time since last session.
Yes. It's been having issues starting Zoom, but I think it's finally working now on this end. Okay. Let me just get it ready. Is everybody's microphone working?
Yes. Hi, Professor Miller.
Hello, how's it going? All right. We go to share the screen. All right, are people able to see?
Yes.
Okay, so what I want to do today is start talking about possible research projects. And so this is an extremely difficult subject to choose problems in because it is so old and so many people have looked at so many things for so long. So to choose projects, we've got to be extremely careful if we want to do something that's original. So part of it is going to be doing some literature review and having you guys look a little bit at what's out there and try to get a sense of what's been done, what hasn't been done. All right. Let's just make sure it's working. Looks like it's not working. Right. Okay. So what I want to do today is talk a little bit about error detection and error correction. So one of the greatest challenges is making sure that the message that you want to transmit is the message that people actually receive. Frequently, you won't be able to confirm easily with the intended recipient that they have received what you wanted them to. And so the question is, how can you build in some redundancy into your message so that you can be sure, or at least reasonably sure, that they receive what you want them to? Now, one of the advantages we have is that when we are building our system, we can often assume that there are powerful computers on both ends. So in terms of what we transmit, we can actually count on the recipient having strong computational powers on their end. So as an introduction, let's review some basics in cryptography. We've talked about this before. So we've talked about how it's not to send zeros and ones. And so let's say we're going to break our zeros and ones into blocks of length 5. So we have 2 to the 5th possibilities. So the letter A will be 00000, B will be 00001, and so on and so on. So the 26th letter, Z, would be 11010, and then we still have a few more numbers. So we could do 0 and 1 for the next 2, and we still have a few more. We could put in maybe some punctuation remarks. And if you wanted more than just 32 symbols, we could, of course, use a string of 6 bits. And then that would give us, instead of 32, that would give us 64, and so on and so on. So here are the 2 big issues. We want to transmit messages so that only the desired recipient is able to read them. So we've talked a little bit about how to do this earlier with different types of cryptography. And the second one, which we haven't talked about, and that's the purpose of today, is to ensure that correct messages are received. And that's what we're going to highlight, and we're going to discuss how to determine, in some situations, if the correct message has been received, And further, if it hasn't, how we can correct it. So let's look back at RSA. So for years, RSA was the gold standard in terms of how to do encryption. One of the things that's so great about RSA, one of the things that makes it so secure, is that when you encrypt a message, you need the entire message to encrypt. And if you change any bit of the message, you're going to significantly change what it encrypts to. So let's quickly go over how you do RSA. So Bob is going to get a message from Alice. So Bob chooses 2 secret primes just to keep the numbers reasonable. Let's take P to be 15,217 and Q to be 17,569. And then Bob chooses a D for decrypt and an E for encrypt. And he keeps D, the decrypt key, secret, and he makes E public. And E and D satisfy E times D has a remainder of 1 when you divide it by P minus 1, Q minus 1. So it's 1 mod P minus 1, Q minus 1. And Bob makes public the product of the 2 primes, which here is 267347473. And now let's say Alice wants to send Bob a message. So the message could be anything from 0 up to n minus 1. It's going to be relatively prime to n. And again, in applications, we want our primes to be of size, say, 200 digits. So each message would be a 400-digit block. This is obviously much smaller. I want to fit it all on the screen. And so Alice chooses 195632041, calculates m to the d mod n. So we use fast multiplication for this, so it can be done quickly. And she sends 121209473. And then to decrypt, all Bob has to do is just raise that to the eth power, and the message comes back out as you would expect. Imagine, however, there was a transmission error. And instead of receiving the correct message, the second to last digit is changed. And rather than receiving a 7, Bob receives an 8. So Bob receives 121209483. So Bob tries to decrypt this message. So Bob raises this to the D for decrypt, and out comes 195632041. I'm sorry, that was the original message. What comes when Bob decrypts is 121141028. So if you look at this, only 2 digits were correct. This is a huge advantage over a lot of the alphabet codes we did. Back then, if you made an error, that's not a big deal. You get 1 letter wrong. Here, everything is now blended together. And if you make a small error, it's going to propagate. Are you surprised that 2 of the digits were correct? Does that seem reasonable? Is that high? Is that low? What are your thoughts? So what do people think?
The error itself is huge.
The error is huge, but are you surprised that 2 of the digits were right? Would you have expected none of the digits to be right? So whenever you see anything, you always want to be asking, is this reasonable? Am I suspicious or not? Very small patterns is often the entrance to a successful attack in cryptography. What do you think the odds are that 2 digits, a digit in the message that's correct and the difference in the message that we think was sent, what do you think the probability is that those 2 digits are the same?
One out of 10?
Excellent, 1 out of 10. if you assume that the process is so large and complicated and that all the digits are equally likely, it's reasonable to say there's about a 1 in 10 chance that 2 digits will end up being the same. So roughly every 10 digits, we would expect to have 1 correct. And if you look at the size of our message, 1, 2, 3, 4, 5, 6, 7, 8, 9, you would expect to have about 1 digit correct. We have 2, but this is a really small count. No extra observation is going to change the percentages tremendously. So we would expect, since we have 9 digits, we'd expect 1 of them to be right, 2 of them, it's a little high, but it's not dangerously high. So I would like to see a larger message, and if you want, this is a great exercise you can do, is take bigger primes and do this again and see about how many digits correct would you get. But this is a reasonable amount. I'm not surprised by this many digits being right. Of course, we don't know which digits are right when we are decrypting this. And so the problem is, we were off only by 10, which is small relative to the size of the number, but it was enough to completely change the message. So while this might make us feel good in terms of security, it's bad in terms of just trying to understand what was sent. It means that a small bit error is enough to completely destroy the message. So we're going to concentrate on error detection and error correction. So of the two, the detection is the easier one. The detection is just noting that something wrong has happened, knowing that a mistake was made. The harder part is then fixing things. So we're going to start off with a couple of different approaches, and then we're going to end with some avenues for future research. And then, if time permits, we'll talk a little bit about some other applications along these lines. So out of curiosity, has anybody heard of check digits before?
No.
You mean repeat a digit by 3 times? Like if you want to transmit one, it's 111.
That's not quite the same thing as a check digit. So check digit is different. It's similar. So what you want to get a sense of is how difficult is the calculation? And depending on how difficult the calculation is, you have a different desire or willingness to repeat it if necessary. So have you ever been to a supermarket with a laser scanner at the checkout?
Yeah.
So in my mind, this is one of the greatest inventions of the 20th century. So the clerk doesn't have to know the price of most items. They simply take your item, they scan it, and then you're charged the correct amount. But when the scanner reads the item, it automatically updates the store's inventory. So the store now knows what's being purchased and can keep track about when is it necessary to order more. Further, most people have rewards cards that stores get you to obtain. If you use the rewards card, you get additional discounts. What they really want to do is they want to link your purchases to you, and they want to see what correlations are there. If you buy X, what else do you buy? There was an interesting story a few years ago at the chain Target, where somebody in one of the Midwestern states was very upset because he got some coupons from Target about baby products. And he was quite upset because he and his wife were well past the age of having kids. His daughter was in high school, she was too young. His son was in junior high, he was too young. Why am I getting all these baby coupons? He was very upset. The manager apologized, gave him a gift card. And then a few days later, the manager called him up to see how everything was doing. And the man sheepishly apologized and said, actually, it turns out those baby coupons are useful. I didn't realize what my high school daughter was up to, and she's pregnant. Target was able to figure out that he was going to be a grandfather before he knew it. And it was coming from looking at correlations in purchasing. And what Target noticed is that the purchases the daughter was making correlate extremely well to someone who was pregnant. And they wanted to try to maximize their chance of getting their purchasing, so they wanted to give them coupons to make going to Target desirable. Now, what Target wants to do is they want to keep people coming to their stores as much as possible. So they want to send great coupons. They don't want people to feel like they're being deliberately targeted. So what they did now, which is really clever marketing, is they looked at some items that would be anti-correlated with pregnancy. And they put those in as well. And then they just put in a bunch of random coupons. So they put in a bunch of coupons that would clearly not be applicable. So it would look like, oh, it's just a hodgepodge. It's just a mismatch of coupons. But they would make sure that the key ones are still there. No, this is all coming from the ability to just quickly scan an item when you're checking out and take that information and do things with it. But what happens if the scanner goes wrong? You scan it and it doesn't read it properly. What does the clerk do?
Scan it again?
Yes, scan it again. There is no need to have a complicated system at a supermarket. It's very easy to scan it again. All you need to do in this situation is just detect that an error was made. And that's why for problems like this, you want to get a sense of how much effort is it worth to fix things versus just, let's just do it all over again. It's so easy to rescan, just rescan. As an example where it might not be useful, imagine you're the captain of a nuclear submarine. You need to keep your position secret. But maybe every now and then you need to surface to get orders. You want to be surfaced for as little time as possible. So you might quickly surface, get a message, and then go back to the depths. You don't want to broadcast your position, so maybe you're just receiving. If you get an incorrect message, you can't easily communicate to headquarters your situation. So in a situation like that, it is very difficult to communicate. In a situation like that, you don't want to have the message resent. You want it sent just once, so you want to make sure not only do you detect an error, but you also correct an error. As another example, let's imagine you're trying to download some information from the internet. So the internet is much better than, when I was younger in terms of just how much information can be downloaded. You don't want to download, a gigabyte file and then find out only after you've downloaded it all that there was an error somewhere and it's not working. You want to constantly do checks as you're downloading things to make sure everything is correct. So what I want to do first is talk a little bit about how you can detect an error. So always think scanner in the supermarket. This is a situation where it is easy to detect errors. So all we need, since it's easy to retransmit, is just detecting at this point. So the first idea is a check digit. And I've written it both doing it in base 10 and base 2. And the idea is the following. So the pink digits, 9134 in the first and 1101 in the second, that's going to be our message. And the last one, the blue, is going to be the check digit. And we're going to choose a digit so that the sum is 0 mod 10, so it has no remainder when we divide by 10, or it's 0 mod 2. So is it always possible to choose the blue number? And if so, is the blue number unique, or is there more than one choice? What do you think?
Unique.
Yeah, unique. Why is it unique?
Because if there is a one number that sums up all 5 numbers equals 10 or 20 or 13, if there exists another number, it might be the first number plus 10 or plus 20 or so. So that is higher than 10.
Okay, that's the key thing. Is if two numbers work, they have to differ by a multiple of 10. So if the first 4 digits sum to something that has a remainder of 7, then you have to add either 3 or 13 or 23, et cetera, et cetera, et cetera. And so since you can only add one digit, there's only going to be one complementary number. So the trick digit is a very easy way to see what's going on. Okay. So if you look at this, this is the correct transmission. Now let's look at this. So imagine I received 92343 or 11010. Could those messages be correct? So is it possible that the message was correctly sent in both cases?
Yes.
Okay, so why is it possible? So why yes? So you said it's possible. So why is it possible that this is correct? So what's supposed to be true about our check digits?
Only the first
All sum either 0 mod 10 or 0 mod 2. Let's look at the first one. What do those 5 numbers sum to?
20.
Try again.
21.
They sum to 21. What about the bottom? What does it sum?
3.
3. So if the check digits, if the message was correct, then the sum of the digits in the top has to be a multiple of 10. It's not a multiple of 10. If the second message was correct, the sum of the digits has to be a multiple of 2. It's not a multiple of 2. So in both cases, there must be an error. Where is the error? Unfortunately, we don't know. It could be in the check digit, or it could be the message itself. So if we go back, the message was supposed to be 9134 in the first. We got 9234. So if we had 9134, the check digit should be 3. So 92343, the error is in the 2. But we don't know that. For the second message, we meant to have 1101, which would have a check digit of 1. We got 11010. So in the second one, the message was actually correct. The error was with the check digit. So unfortunately, in a situation like this, we don't know where the error is. We don't know if the message is right and the check digit is wrong, or the check digit is right and somewhere in the message there's an error. Right. There are more involved methods possible. So I've given you a link to a more powerful algorithm which not only can catch a single digit error, but can also catch flipping adjacent digits. So if you have 314 and accidentally send 341, this method can detect stuff like that. The problem is these methods can only detect. They can't correct. So we want to do more than just detect We want to detect where the error is and then fix it. Now, what's nice is if we do things in binary, is it enough to just find the location of the error? What do you think? In binary, is it enough to just know where the error lives?
Yes,
Yeah.
Why?
because it's not zero. It is either 0 or 1.
Okay, good. So if there's an error, then it has to be the other digit. So there's a brilliant comedy called Seinfeld. And in Seinfeld, there's a character named George Costanza who loses sadly. And one day he remarks to his friends that every decision he's made in his life is wrong. His friends tell him, you know, if every decision you make is wrong, then the opposite will be right. Now, unfortunately, in real life, you can have more than 2 alternatives for things. But for the rest of the episode, he resists his natural temptation to do what he thinks is right, and he does the opposite, and his life improves dramatically. In the real world, you can't do this. In the real world, there's far more than 2 options for most things. But this is a huge advantage of binary. So transmitting digits. What is the best probability for success for transmitting a digit? So let's let P be the probability that I receive the digit you want to send. What would you like the probability of a successful transmission to be?
1.
1. You'd love it to be 100%. What is the worst probability for transmitting a digit? So what would be the worst probability? If 100% is the best, worst. Could you say that again? I couldn't hear you.
Is it 0?
So you think 0% is the worst
Oh
probability?
no, 50%.
Ah, it's 50%, not 0%. Why is 0% okay?
0%. It means like 0% is exactly the same as 100%.
Exactly. As long as you know that the probability is 0%, then you know that everything you do is wrong. And so just do the opposite. Just think like that, funny Seinfeld episode. So the worst is 50%. If you have a 50-50 chance of being right or wrong, then you have no idea what to do if you receive a digit. It's as likely to be right as it is to be wrong. So that's going to be the absolute worst in terms of trying to get a sense of information. So the first is to try to detect where the error is. And one way to do this is what's called the tell me twice. So we promise our receivers that we will only transmit the messages 1, 1, and 0, 0. We're not going to transmit anything else. So we basically double our message. So if you receive 1, 1, or 0, 0, that's great. It's possible that we had a huge error. Maybe we meant to send 0, 0, and we accidentally sent 1, 1. That would be a 2-bit error. We will assume that errors are extremely rare, and that's extremely rare that we make 2 errors in a small transmission. This is an important assumption. You can drop this. You can come up with methods that will detect if there are 2 errors or 3 errors, but those are more cumbersome, and they require more of your message to be spent on detection and correction and less on data. So for now, if we assume that it's very unlikely that an error is made, which is a reasonable assumption as otherwise you wouldn't be transmitting in this way, then if we receive 1, 1, we can be pretty sure that we meant to send the message 1. And if we receive 0, 0, we can be pretty sure we meant to send the message 0. Now, if we get the message 1, 0, we know that a mistake was made, but we have no idea where. It could have been the first digit, it could have been the second digit. So the simple solution, as was remarked by somebody, is called majority rules. So now we transmit 3 bits. We transmit 111 or we transmit 000. And now, if you receive 101, for example, or 100, we see that they don't all agree. So we know, since we promised we're only going to send the message 111 or we're only going to send the message 000, we know that both messages have a mistake. And by assumption, since we're assuming it's very unlikely that an error is made, what do you think 101 was probably supposed to be?
1.
Yes, probably supposed to be 111. And similarly, 100 was probably supposed to be 000. So majority rules is actually not bad. It allows us not only to detect an error was made, but where the error was and to correct it. So what do you think? Is this a good method, yes or no?
There will be more data transferred, which may take longer time.
Yeah, so it's going to take longer to transmit your message. In fact, what fraction of your message is actually data, and what fraction of it is error detection and error correction?
It's only 1/3 is the data.
It's only 1/3 is data. What would you say is a good critical threshold to be acceptable? What fraction of your message should be data at a bare minimum? I think half is reasonable as well. If you can't say that at least half the time, at least half of the message is data, it seems like you're spending far too much time on the detection correction. And so to me, the critical threshold of success will be, when is our method good enough so that at least half, even better, more than half, of what we transmit is actually data rather than mathematical stuff to make sure everything is good. So the tell me 3 times has some serious defects. It's great at correcting, but it's very expensive. And because it's so expensive, we have a desire to do better. All right, so before going to the better, I believe these are the Seinfeld episodes I was talking about. And as you remarked, only 1/3 is information. So how can we do better? Well, the first thing is, well, what if we do tell me 4 times? This is going in the wrong direction. It's not making things better, it's actually making things worse. Now only 1/4 or 25% of the message is data. And in the general case, tell me n times, only 1/n, 1 out of every n bits is data. So this is not the way to go. We need a better way than just tell me more and more times. So now we're coming to the research project that I wanted us to look at together. We need to find better ways to transmit information. And the problem is, the first approach we have is just too expensive. Too much of our time is spent sending extra bits of information to do these checks, and only 1/3 or even worse is actually messaged. So how can we get better than 50%? So let's revisit the tell me 3 times. So the pink digit for today is always going to be the data, the blue digit's always going to be the checks. So I've rewritten the 3 points in 2 different ways. The first is having it all in a line. The second is making it into a triangle. Does it matter how I present the stuff geometrically? Is it still the same method? Yes or no?
I don't think it matters.
It doesn't matter.
Right.
But I can now view the second picture a little bit differently in terms of how I choose things. I can view this as 2 tell me twice methods, a horizontal tell me twice and a vertical tell me twice. It has the same net effect. But now, imagine that there's a mistake in the first one. So imagine these numbers here don't sum to 0 mod 2. Imagine this is an odd sum. Then you know there must be a mistake in here. Similarly, if this sum is odd, you know there must be a mistake here. So you can use this to try to figure out where is the mistake.
How can you transfer, but how can you transfer a shape like this? Do you like use matrix?
So in terms of transmitting the shape, on my end, when I'm receiving, I can have this shape over here. The first number you transmit, I put in here. The second number you transmit, I put in here. The third number you transmit, I put in here. I can just have a rule already established as to where things go. On your end, you can just keep sending a string of numbers, and I just know how to place every number in a pattern. So you still just send a string. And now, if this is odd over here, and this is odd, I know there's a mistake in this column, I know there's a mistake in this row, that means this has to be the one in error, because we have at most one error by assumption. If this is odd, and this is even, I know this column is correct because it's even, this row is wrong because it's odd, that must be wrong, the check digit. So looking at it this way allows us to detect the error and correct the error. And so I'm going to just draw this with arrows. So the first arrow here is telling us we're going to use this as a check digit for tell me twice horizontally. This arrow we're going to do a tell me twice vertically. So let's imagine now we want to transmit 2 digits of information. So I put my 2 digits down here. This bit is going to be a check digit horizontally. These two are going to be check digits vertically. If this works, what fraction of our message is information?
40%.
40%. That's better than 33%. It's still below a critical threshold of 50%, but it's better. And with a little bit of analysis, I encourage you to do this, you can show that this will detect and correct any 1-bit error. So imagine that this second pink dot is wrong and everything else is right. If that second pink digit is wrong, you're going to detect an error over here in the first row. There'll be no error detected here, so these are both right. There'll be an error detected here. So if there's an error in this column and an error in this row, it must mean that this pink thing is wrong. Conversely, imagine that this digit is wrong. Then you'll get that there's an error in the first row. The first column looks good, the second column looks good, so the error has to be here. And you just go through this for the other remaining points, and you see that it works. So this is much better. But it's not, unfortunately, 50%. Could we extend this further? What do you think? So do you think we could extend this further?
Like if we make more like the real data, like if we add the real data to be like maybe 3 or 4.
Yes, we could just keep adding more columns. And in the limit, what fraction of our message would be data? What would it be approaching?
Approaching a half.
It would be approaching a half. Unfortunately, it would always be strictly below a half. And unfortunately, we would be having a tremendously large amount of points that have to be transmitted together to get closer and closer to a half. The more points we transmit, the more likely it is that we make 2 errors, not just 1 error. So unfortunately, this approach on the bottom, while it does better, it can't be the final answer. So does everybody understand that that can't be the final answer?
Yes.
Okay, so the important thing to remember is when we're transmitting, we don't have to worry about the geometry. The geometry can just be on the receiver's end, and you just fill in stuff. So you fill in 1, 2, 3, 4, 5, something like that. You have some predetermined rule as to how the stuff is filled in. All the transmitter has to do is send the numbers. So unfortunately, this geometric approach does not work. So we said it's 40%. It's still below 50%. In the limit, it can get close to, but it will never be 50%. And then the question is, how can we do better? So one possibility was to try to do 3 points and put a point here, or 4 points and put a point here, here, and put up more stuff like this. That can't work, so we need something better. So we should try transmitting 3 points, transmitting 4 points, transmitting 5 points of data, and seeing how should we put the check digits. So does anybody have an idea of what shape we might want to use if we transmit 3 data points?
A triangle?
A triangle, outstanding. And if we use 4 data points, what kind of shape?
A rectangle.
A rectangle or a square, outstanding. So here is a triangle and a square, or at least here's one way of doing it. There's more than one way of writing these pictures. And the idea is you have the phrase, a picture's worth 1,000 words. If this is done correctly, you should be able to quickly look at this and understand what's going on. So everything that's pink is data, everything that's blue is a check digit, and the lines tell you which points are connected. So over here, because these 3 points are on a line, this is a check digit for these 2. Since these 3 points are on a line, this point here is a check digit for these 2, and so on and so on. So which do you think is better? The picture on the left with the triangle, or the picture on the right with the square?
They're both the same.
So they're both
50%.
They both transmit 50%. So the first thing we need to do is go through and make sure that it really works. So I'll just do 1 or 2 things. Imagine this digit is wrong here and everything else is right because we only have 1 error. If this digit is wrong, this line has a mistake and this line has a mistake. The unique intersection of those 2 lines is here. Imagine this digit is wrong. This line is wrong. The other 2 lines are correct, so this must be the error. Similarly, if we come over here, imagine this is the one unique point that's wrong, then this line has an error, this line has an error, the only point the 2 lines intersect is right here. If this point is wrong, then this line is wrong, everything else is correct, so the error must be here. So if you go through the algebra, both methods allow you to detect and correct 1 error. And both of them are 50%. So we at least hit the goal of 50%. So does anybody have a preference between the triangle or the square?
I think triangle is better
So why is the triangle better?
because it contains three bits of information, but the square contains 4. So there's more possibility for the square to make 2 mistakes in the structure.
Right, because for the triangle, we're bundling 3 bits of data with 3 bits of checks. It's a set of size 6. It's going to be less likely to have 2 errors than something with size 8. So they're both good. In terms of just arranging the geometry, would you rather work with a triangle or with the square?
A square?
Yeah, I think the square is a little bit easier to visualize and work with. You can work with either, but I think the square just feels nicer. But for the computer doesn't care. You can program everything. And because you can program everything, it's better to use the triangle. So now, what should we do next? 5 points, 6 points, 7 points, 8 points, 9 points. What do you think we should do? 5 is the next number. We just did 3 data points, 4 data points, so should we try to do 5 data points? Or do you think other numbers might be easier?
Six, maybe.
Why 6?
Because you would get like a perfect square of data points and like a triangle.
Oh, you're very careful. You said a perfect square, and then you said a triangle. Which is the shape, a square or a triangle?
A triangle.
A triangle. So there's such thing as the triangle numbers. The first triangle number is 1. The next triangle number is 3. The next triangle number is 6, then 10. And what you do is the nth triangle number is 1 plus 2 plus 3 all the way up to plus n. So you have, the first row has 1 dot, the second row has 2 dots, the third row has 3 dots, and so on and so on and so on. So triangles are very nice. The number of points in the nth triangle number is n plus 1 over 2. So one possibility is to go for 6. What's another possibility for what might be nice to go to?
I guess 9.
Yeah, so I guess 9 would be the other one, is to go from the 2 by 2 square of data to the 3 by 3 square of data. So there might be things you can do for 7 and 8. There might be things you can do for 5, but it does seem like the next natural generalizations from these two would be to the next triangle number and the next squared. But for the stuff to look at for projects, or at least for some preliminary work, try to consider 5, 7, and 8 and see what is the best pattern you can do for there and what's your efficiency. Now it gets a little bit harder to draw things, at least for the triangle numbers. For the square, it's not so bad. And you can see how easy it is to draw things with the square. And again, if we choose, say, this point to be the only point that's wrong, then you would get an error for this line. You'd get an error for this line. All the other lines would be right. So the unique point that's on this line and this line is the one right here. For the triangle number, here is one way to draw it. So I've got a couple of lines with just 3 points of data and 1 point of check digit. I have this one, I have this one over here, I have this one coming down here. And notice that each of these points over here, well, let's see, this is on 2 lines, this point's on 2 lines, this point is on 2 lines, but the 3 middle points are only on 1 line. Well, lines right now have 3 data points and 1 check digit bit. So I could take these 3 points here and say, I'll take those 3 points and put a check digit bit for those. And here's a shape that works. The problem with this is, what do you think, like if we now go to the next triangle number to 10? The picture's going to get a little bit harder to look at. But we'll deal with that in a moment. So both of these give 60%. So for the triangle, we have 6 bits of data. We have 4 check digits, that's 60%. For the square, we have 9 bits of data, 15 pieces of information transmitted. So 9/15 is the same as 3/5, so 60%. Which do you prefer, the triangle or the square? So what is your preference, the triangle or the square? Or do you not care because both of them give 60%?
Well, I prefer the triangle because it only has 4 lines.
It's not that it has 4 lines. Why do you prefer the triangle? It's not 4 lines. It's close to that. What's better about the triangle?
It contains a smaller amount of pink points.
Well, it contains a small number of points. It gets the 60% using fewer points. And the more points you have, the more likely you are to have 2 errors. So for that reason, I prefer the triangle. In terms of just doing the algebra, the square just sets up so much nicer. But even though it sets up nicer, I would much rather have fewer points, and I can just hard code the algebra. I just have to code which 4 things are bundled together when I'm trying to calculate my check digit. And so, I've written on the top the formula for the nth triangle number and the nth square number. The formula for the nth square number is pretty obvious. The nth triangle number is often proved by induction. So here's another way of trying to write the graph for the triangle. So could somebody tell me why this might be better?
Easy for programming?
Well, in what way is it easier for programming?
Because when the amount extends to larger size, it have its own rule to program.
Right, so we want something where the rule is going to be very clear. If you look at the beginning, here is my 3 bits of data, and here are my check digits, here, here, and here. So what I'm doing to get to the next level is I change my check digits to information, and then I continue each of those lines. And then I take those 3 check digits, and I connect them, and I make a new thing over here. And just a little bit hard to draw, but then what you would do for the next level is these would all become bits of data, and you would continue all those lines or curves, and then you would connect these ones as well. And so, just being very explicit, a triangle number is going to have n plus 1 over 2 bits of data that we are transmitting. N plus 1 of these are checks. So you can calculate out of how many bits of information it will be total, and you can see that n over n plus 2 is going to be information. You get the same ratio for the square. You have n squared pieces of data. You have 2n check digits. So you have n squared plus 2n bits total. So when you take n squared and divide it by n squared plus 2n, you get just n over n plus 2. So they both have the same efficiency. So we can get as high of a percentage as we want, just at the cost of larger and larger strings. So in the limit, can we get up to arbitrarily close to 100%? Yeah, because the information, the efficiency is n over n plus 2. So n to be 8, you would get 8. That's pretty good. So is there a better geometry that we can use? That's the big question. So how many of you have experience with Rubik's Cubes and know how to solve Rubik's Cubes? Any Rubik's Cube fans? Okay, so I guess it's just me. So I am a huge Rubik's Cube fan. I'm actually building my own Rubik's Cube right now, just for fun. Let's try to think about what would happen if we tried to extend this to a higher dimension. So imagine you have a 2 by 2 by 2 Rubik's Cube. So how many pieces do you have? Well, we have 4 pieces in the top, 4 pieces in the bottom, so we have 8 pieces total. If we have a 3 by 3 by 3 cube, we have 27 data points. 9 in the top row, 9 in the middle, 9 in the bottom. Is everybody good with these numbers?
Yes.
Yeah.
Yes.
Okay,
Yes.
so what we want to do is we want to try to figure out what would be the generalization. So if we go back a page, or I guess 2 pages, what we saw we were trying to do is figure out which row, which column. That's where the check did row and column. Well, now, in addition to row and column, we also have the height. So the idea, when we just had, say, just the top over here, we would have a check digit here and here to get the 2 rows, and a check digit here and here to get the 2 columns. So I'm claiming that for the 2 by 2 by 2, we have 8 data points, and we only need 6 check bits. What would you do for the 6 check bits? Can anybody tell me how we would do the 6 check digits for the 2 by 2 by 2 cube? So I will give you a moment to think about this.
Is it like the 2 vertices across will be the ones that are not the check bits, and the rest will be?
Well, we want the 8 pieces of the Rubik's Cube to be the data. So we have this piece in the corner, this corner piece, this corner piece, this corner piece. So you have 4 pieces on the top and 4 pieces on the bottom. Those 8 pieces are going to be the data we want to transmit. What you have to tell me is, how do you choose the values for those 6 check bits?
Center of each plane.
Okay. Well, instead of center, you can just say, I want a check bit for each plane. How many planes are there?
6.
6. So you have 2 horizontal planes, the top and the bottom. You have 2 planes like this, the front and the back. And then you have, what's your name? So we've got, top and the bottom is 2, front and the back is 2. And we've got this way and this way. So we would have like the white face and the face behind the white face, which is different than the orange face and the face over there. So because there are 6 planes, each plane gets a check digit. And if the check digit is wrong, you know that there's an error in this plane. So for each possibility, we're going to have 5 points bundled together, 4 pieces of data and a check digit. So if there's a mistake, it's either in the check digit or it's in one of the 4 points in that plane. So imagine the check digit from the orange plane plus the 4 orange points is not 0 mod 2. Then we know there's a mistake somewhere. It's either in the orange plane here or it's in the check digit. Now imagine when you look at the 4 points in the blue and the check digit here that there's a mistake. Then you know it's either in one of the blue points or the check digit. But because we're assuming there's only one mistake at most, then if there's an error, it's in the blue plane and its check digit or the orange plane and its check digit. So what are the only two places it could be?
Two vertex on the top,
Yeah, what colors?
orange and blue.
Yeah, it's got to be one of the orange two ones. Now we look at the check digits for the front and the back. If the one for the front is wrong, if it doesn't add up to 0 mod 2, then the error is either in one of the four whites or its check digit. But we already know the error is in one of these two. The only thing that works is the one in the upper corner. And so by looking at the planes, if 3 plane check digits are wrong, that's going to uniquely specify a point. So, really good exercise is to go through this slowly and convince yourself that this is correct. What about the 3 by 3 by 3? I claim we need 9 bits for the checks. Why do we need 9? So can somebody tell me why we need 9 bits?
Because 1 bit for each plane is not enough.
So how many planes do we have for the 3 by 3 by 3 cube?
It's still 6.
Okay, so why are there 6 planes for the 3 by 3 by 3? So if there are 6 planes, you have to tell me what the 6 planes are. There were 6 planes for the 2 by 2. If there are also 6 planes for the 3 by 3 by 3, do you think there'll also be 6 planes for the 4 by 4 by 4? So somebody has said that there's still 6 planes. Can you please tell me what those 6 planes are? This is wonderful if we could be in the same room so that you could just go to the blackboard. But can somebody start to tell me where, if you can't tell me where all the 6 planes are, tell me where at least some of the 6 planes are.
Is it just one side of the cube is one plane?
Okay, so let's choose a side. Which side do you want to look at first?
Orange, maybe?
Okay, so the orange plane is going to be 1. So this is going to be a plane that is maybe, we'll call that one of our vertical planes. Are there any other vertical planes?
The plane behind the orange one.
Which plane behind the orange one?
The opposite plane.
Which one is the opposite plane? Is it this one in the back? Is that what you mean, this one?
Yes.
Okay, so that's our second vertical plane. Are there any other vertical planes?
And the one opposite to the white.
That's not going to be in the same direction as these two planes, right? The orange plane and the one behind it, if you know your Rubiks Cube, you can figure out the color. That would be the red plane. We'll call both of those our vertical planes. Is there any other vertical plane that's parallel to those two planes? We have the orange over here. We have the one all the way in the back. Is there any other?
No.
No.
Okay, are there any horizontal planes?
Yeah, the white.
So
The
what
white one.
plane? So you've got to tell me, what do you think the horizontal plane was? On the 2 by 2, it was the bottom and the top. What will it be here now?
It will still be the bottom and the top.
So it'll still be the very bottom, and it'll still be the very top. Are there any other horizontal planes, or is it just the top and just the bottom?
Just the two.
Okay. And then similarly, we had the front and the back. So you'll also have the front over here, the white, and the one behind it, which would be yellow. And so that's our 6 planes. I'm claiming, however, that there are 9 planes. So you're missing 3 planes. You're missing a vertical plane, a horizontal plane, and a front and back plane.
Oh, the one sandwich between the.
Yeah, the one
Sandwich
sandwich between. So
Okay.
this is fascinating that everybody missed this for multiple times. Because this is recorded, you can actually go back and see just how long we spent thinking that there were 6. And I really want you to think later tonight as to either why you missed these, or if you had them and you just didn't want to risk saying them out loud because you didn't want to look like you were making an error. You know, I've noticed a lot of people are silent. And if you don't speak up, nobody will see you making an error, but nobody will also see you making a good observation. And so I really want you to get to the point in life where you feel comfortable enough to try to say, hey, I think this might be the answer for the following reason. We spent a lot of time missing the 3 planes coming from the middle. And so I really want you to think, if you were fooled by this, if you didn't see them, where was the source of confusion? Why were there such blinders that you didn't see this? You know, I'm telling you that there's 9. I'm saying we need 9 check bits for the planes. And everybody keeps saying there's only 6, there's only 6, there's only 6. So now, if I give you 9 check bits for the planes, let's look at the check bit for the orange. So we have the 9 data points here plus 1 point here. If there's an error, then it's not going to sum to 0 mod 2. So it's either one of those 9 points or it's the check digit. If I look at the white plane now, and its check digit, if that is 0 mod 2, then I know those 10 points are correct, which means it can't be these 3 oranges. If I look at the middle plane now, the middle front back one, if that's wrong, then I know now it's one of these 3. If I look at the blue top and I know that's wrong, then it's going to be this one over here. So very similar to the previous calculations, you can now go through and show that this is going to uniquely specify an error. And what goes on is that the data points, the 27 data points, each point is on exactly how many planes?
Exactly 3.
It's on exactly 3. And then the check digits are all by themselves. So there's a little bit of a loss there, but that's okay. So in the first one, when we have 8 data points, we have 6 check bits. So that's 8/14 of 57%. Is that good or bad?
That's better because it has higher accuracy and a higher percentage of information.
Okay. What should we compare this 8/14 to? So what were we looking at before we went to 3 dimensions?
The 6 and 9.
Yeah, the 6 and the 9. So with the 6 triangle points, we had 6/10, which was 60%. So how does this square compare to that? Is this better or worse?
I guess the 8 data points is worse.
Yeah, the 8 data points is worse. Now for the next, we have 3 by 3 by 3. That's 27 data points, 9 check bits. So it's 75%. If we did a 6 by 6 square, we would have 36/48 or 75%. If we used the 7th triangle number, it would be 28 out of 36 or 77.78%. So the 3 by 3 by 3 square is already doing better. I'm sorry, the 3 by 3, yeah, the 3 by 3 by 3 cube is already doing better than the square in the plane. Here, they both hit 75%, but the cube only needed 36 points, the square needed 48. The triangle number is doing better than the cube, but not by much. It's transmitting 1 extra bit of data. Now, instead of looking at a cube, what might you try to look at in higher dimensions? Like 3 dimensions. What shape might you look at? All right, since it's getting late, I will leave that as something for you to think about. Let me see about just doing one more. I'll just do one more. So we'll stop here and then we'll continue this the next time. If we did the 4 by 4 by 4 cube, there'd be 64 data points. And then as a nice exercise, show that there will be 12 check bits. So there'll be 4 vertical planes, 4 horizontal planes, and 4 front back planes. So that's 64 out of 76, or 84.21%. We did a 9 by 9 square. That's 81/99 or 81.82%. If we did a 11 T11, the 11th triangle number, that'd be 66 data points, and the info is only 83.54%. So we're now at the point where the cube is beating the triangle. The 3 dimensions is beating the 2 dimensions. In our last lecture, we will then really get into the detail of what your research project is going to be. It's to try to find the best geometry to get the best error correction detection. Now, these methods will not beat what is currently being used. Those use more powerful methods, but what we're doing here is very easy to write down what's going on. Advantage of stuff like this to just see what the geometry will be. All right, so this is a good place to stop. I apologize once again for the issues in getting Zoom to start. And if you have any questions, just shoot me an email. I will see now if I can actually exit the meeting. Okay, any last questions?
So Professor Miller, I wonder, as an analogy, if you can use cubes in 3 dimensions, can you use triangular pyramids?
So that would be a very natural thing to look at, is to try to look at triangular pyramids and how efficient they are. So it's a great thing to look at.
Okay, thank you.
All right. I will try to get the video posted. Have a great evening, all.
Okay, thank you very much.
Okay, thank you, Professor Miller.
Bye-bye.
Yes, thank you. Bye.